The module 2, the multi-carrier modulation. Today let us have a discussion about spatial diversity overview. Okay, here spatial diversity overview. The spatial diversity, already we have known that two or more antennas will be placed, which will be separated by the specified distance to avoid the fading and also to decorrelate between them. So, what is the advantage of spatial diversity? Is no additional bandwidth or power is needed when we go for the space diversity concept. Now, there we need to some additional antenna we have informed on name, but this additional antenna also is limited by the need. Okay, so radio frequency transmit and or receive chain and also a digital signal processing are required to modulate or demodulate the multiple spatial streams. And here we are using multiple antennas now in the spatial diversity. So there will be two major parameter we have to know. One is array gain and another one is diversity gain. So if we come to the array gain, so array gain means antenna will be placed in the form of antenna arrays. So the last module we have seen that there are two types of antenna array techniques. One is end fire antenna array, another one is broadcast antenna array, broadside antenna array. And in the module 1, if we are seeing the topics, we have chosen a broadside antenna array. Such a way, here we will see about the array gain. Okay, so what do you mean by the array gain, or what does the array gain means? Okay, so the transmitted signal will have some power gain. Okay, and that transmitted signal power gain will be achieved by using multiple antennas or transmitter. Okay, and also the same thing will be received in the receiver. So with respect to the single input single output case, okay, and it can be simply called power gain, and also in the most of the places we have represented by PG. If it is a receiver power gain, it is PRG. If it is a transmitter power gain, we have represented it is a PTG. Okay, and this array gain will be proportional to the length of the array. So now what this array gain will do, or what the antenna array can explain, if you come to that point, it seems that performance will get enhancement. Okay, because we are coherently combining the energy of each of the antennas to gain the sum of the advantage versus noise signal on each antenna. So first thing is the system performance, or the communication performance or signal performance will be enhanced by coherently combining the energy. So followed by this array gain for correlated channels we will see. So these antennas are placed in the form of array, and the channels are completely correlated. Correlated is nothing but LOS system. We will be talking about the LOS system, that is nothing but line of sight. So the received signal to noise ratio increases linearly with the number of receive antennas, that is NR. Now here the main parameter is signal to noise ratio, and this signal to noise ratios will increases linearly the number of receive antennas N suffix R. Now if you think about NT into NR system, that is number of transmitting antennas as well as number of receiving antenna system, the array gain is NR, so that for each antenna, that way I is nothing but equivalent to 1 comma NR, and this will receive a signal that can be characterized such a way yi is equal to Hix plus Ni is equal to Hx plus Ni. Yi is equal to Hix plus Ni. That is, it can be written as Hx plus Ni. We will see what is Hi. Hi is nothing but that is the height for the all the antenna since they are perfectly correlated. So this Hi can be written as HR. For example, we are using n number multiple antenna. This I vary from 1 to n. So H1, H2, height of the antenna of antenna 1, antenna height for antenna 2, height of the antenna 3. Like that is I varies from 1 to n. But here we are saying Hi can be represented by H because all the antenna heights are perfectly correlated. Okay. Now signal, you are in a position to know the signal to noise ratio on a single antenna. Signal to noise ratio on a single antenna. If we come to that point, we will take gamma I is equal to modulus of H2 divided modulus of H divided by 2 by sigma 2. It is nothing but the noise power of each correlated path. Okay. Now, if all the antenna receive antenna paths are added, okay. Now we are first, what for analyzing purpose, what we will do, we will calculate individually. Then we will take 1 to 5. Then okay, once it becomes stable, we go for the all the receiving antenna path, and we will make a concluded expression. That is nothing but y is equal to summation yi into nri, which is equal to 1, and we all are know that it is nr into hx. We are going to consider the receive antenna path. So number of receive antenna nr into number of antenna heights hs plus summation ni into nri is equal to 0. Now you are, this is for correlated antennas or height or whatever it is. Now we are coming for array gain for uncorrelated channel. Okay, we are assuming that noise on each branch is uncorrelated. Okay, for the branch 1 it will be noise level is high, branch 2 it is low, or that is, so there is no correlation between the noise appearing on the array. That can be written as gamma into summation modulus of nr into h the whole square divided by nr into sigma square. So everyone will get the idea how we are going, we talk about antenna array and how the analysis will be happen, etc. Now coming to the diversity gain. So what is the purpose of the diversity gain? Actually, the purpose of the diversity gain is nothing but to increase the in signal to noise ratio, it is SNR, due to some diversity scheme, or we can call it as transmission power can be reduced. Okay, when one of the diversity scheme is introduced. Okay, and this all happen, but the performance loss will not happen. And also this diversity gain is expressed in terms of decibels. Okay, and sometimes it can be also in terms of power ratio. Okay, so what is the main objective of the spatial diversity? In the sense, it will improve the communication reliability. Okay, by decreasing the sensitivity of to fading. Okay, to improve the communication ability reliability by decreasing the sensitivity to fading. So fading is also one of the main factor, as well as gain, power, everything is important criteria. So one by one, so coming to this, and also we wanted to measure the probability or average bit error rate. So keeping all this in this mind, we have gone through or discussed, analyzed about the spatial diversity. And the bit error probability, it can be represented by BEP, and it can be written on the virtually any modulation schemas, that is PB, so approximately equal to C1 into e power minus C2 into gamma. C1 and C2 gamma are the constant value and all depend on the modulation type. Gamma is equal to received signal to noise ratio. Okay, so what are the types of modulation we are going to use? Based on that, the C1 and C2 will be acting, and gamma is nothing but received signal to noise ratio. Now, fading channel without diversity. The channel is in terms of fading, but you won't have diversity. So this here, the signal to noise ratio becomes a random variable. Okay, in fading channel, so that the bit error probability is also a random variable. So the average bit error probability decreases very slowly, and it can be written as P suffix B is approximately equal to C3 into gamma power minus 1. So hope everyone understood the spatial diversity. Under spatial diversity we have discussed two parameters, array gain and the diversity gain. Thank you.